Okay, so let's get started. So this, I guess these are lots of students. So this week's or whatever, this 2 weeks homework is relatively difficult. So it's totally fine to discuss with friends and so on. And you need a Mathematica to do that. So that if you don't have it, you can ask your friends to run it and so on. And anyway, feel free to use whatever method to solve the problem. Okay, now so we start talking about the interacting theory, and let's recap what we start discussing. So we add. So this is free Hamiltonian. And then we put some interaction term to the Hamiltonian. And in particular, phi 4 theory, we have the phi to the fourth interaction term, and lambda can be understood as a coupling constant. And then we want to understand this interacting theory. To do that, we introduce so-called interacting picture. So instead of the Heisenberg picture, usual Heisenberg picture is e to the I t h o x e to the minus I t h. Okay. So this is Heisenberg picture. But if lambda is very small, the difference between h and h0 is tiny. So that's the idea of perturbation theory. And then, so we just introduced OI. And this OI, interacting picture operator, will satisfy Crank-Gordon equation in the case of the phi 4 theory. So that can be obtained by just acting time derivative on interacting picture, which is I times h h naught O of x. And since we know that the here h naught and h are different is only like a phi to the fourth term. And then phi to the fourth term and phi to the fourth term and phi term commute, we know already. So therefore this is the same as I to the h phi of x. So this is by definition pi of x. By definition. And then you can act again t squared phi of phi I is phi t pi of x. Maybe, yeah. And then this one is again, this is I, of course. Because I missed a lot of stuff. I missed a lot of e to the I t h0. E to the minus I t h0. And you have to add, e to the I t h0, e to the minus I t h0. So therefore, this is phi of x. And then if you sandwich by this one, you get that interaction picture operator. And this is the case. And then we have, again, I times h naught, pi I of x. And we know that the, I have to put this one, I t h0, maybe, e to minus I t h0. And this is, so in free theory, this is nabla square plus m square, maybe minus phi of x, and then you get this one. Okay. So this is just derivation. So since this is the interacting picture operator satisfies the Klein-Gordon equation, it admits the free field expansion like this way, or Fourier modes. And then we define the free theory vacuum as the so AI of P acting on 0. So this is the definition of the free field vacuum. And the question is, what's the relation between true vacuum, so omega is true vacuum in the interaction theory, and then the free theory vacuum. And what is the relation between Hamiltonian and H0, and so on. So that's, so this is, I call, okay. To see that, first we remind ourselves that the OT of X, so the Heisenberg picture and the interacting picture operator are related by related by UT. Just a moment. You have to be careful. 0. Where the U, T and T naught can be equal to e to the I, T minus T naught, H naught, and e to the minus I, T minus T naught, and then H. Okay? So that's the definition of U operator. So they are related by this relation. But just, so this one will cancel with this guy, and create, and this one will create this one. So therefore, interacting picture operator and the Heisenberg picture operator are related by sandwiching by this U operator. Okay? So that's, I already explained last time. And then, for instance, if you take the, so therefore, what we need to study is this U operator. And to study this U operator, take derivative, then what we have is minus I e to the I t minus t naught h naught minus h naught as h, and then e to the minus I t minus t naught h. That's right. So be careful about the order of h and h naught. Okay. They are usually not guaranteed to commute. So therefore you have to be careful about the order. So now we can introduce that the so we notice that this one is indeed the difference is h int. So this is h int. And then so if you introduce the e to the minus I t minus t naught h naught, so then we have to multiply this factor times this factor is exactly U operator, ut t naught, and then minus I e to the I t minus t naught and h naught. Okay? And then we notice that this, since we sandwich by operator generated by h naught, this is indeed equal to, we define as hi minus I, h capital I of t, and u t t naught. Okay, so here we define this one is equal to this one. Okay. And then we call it, this one is interacting Hamiltonian. Okay. And in particular, so you have to be careful of this. So this hi usually do not commute. If you have, there a time dependence, T2 do not commute, okay, usually. Since it's have a 5 photon, but here you have a derivative term and so on. So this has, has the moment, canonical conjugate momentum term and so on. So therefore, usually this HI do not commute if you have a different time. So now we want to solve this differential equation. We want to solve this differential equation. Okay. So to solve that, first we just integrate over so that the so this is differential equation, but differential equation can be written as an integral equation minus I T naught and T HI of T prime, maybe T1 or T prime. Okay. So this is the integral equation. And then we can solve this integral equation recursively. So for instance, if you start, so if t is very, very, very small, so this is, if t is very close to t naught, it's almost 1, right? It's almost 1. Okay, so therefore, so for instance, if you solve it recursively, now we just assume t is very small to close to t naught. Then we have t naught t hi t prime dt. Sorry, maybe t1 dt dt1 dt1. Because I mean here, if t prime is very close to the t naught, it's just 1. And then and u2, and if you move the clock a little bit more, then you have to add hi t2 and u t2 and t naught and 1. So here you just plug this operator into here and so on. So you just do that recursively. So therefore, at the end of the day, what you get is the full solution is given by like this way. 1 plus minus I T naught T, so this is the one. First one is this guy, dt1 dt2 and so on. And plus minus I to the cube, T naught T, T naught D, T3, T2, T naught, DT3, DT2, DT1, and HI, T3, HI, T2, HI, T1, and so on. Last up. Okay. So be careful about here order really matters. So here order really matters because I mean here so usually the interacting Hamiltonian do not commute. So therefore you have to be careful about the order of the Hamiltonian. So just in case we can just I mean, if you want to check this is really satisfy this equation, just take time derivative. So if you want to check it, so you just take time derivative T naught So then what we have is that so we just act the time derivative here, so what you get is the minus I hi of t and plus 1 plus now if you take the time derivative here, again we get the minus I to the hi, but what's left is minus I to the this guy, right? This guy. So T naught, T1, dt1, hi, dt1, plus so on. So then if you act time derivative here, what you get is this hi, which is the same as here, and then what we have is this guy. And so on. This piece is exactly the same as this guy. Okay. So therefore, it satisfies this equation. Okay. So you can just do that recursively integrate over Hamiltonian. Okay. And note that so if you look at the second term. If you look at the second term, so what we have is the so t naught oh, by the way, if you please read the latest lecture note if you always at the overleaf. Otherwise, I always keep updating the lecture note. So if you don't for instance, don't download don't look at the old one. Yeah. So here, this is T2. Sorry. Okay. So here what we need to do is this is T integral, T2 integral, and this is T1 integral. Okay, and then T1 integral cannot. So this is diagonal line. And then, so here, this means that the T0 to T means that T1 integral is always T1 direction is here, right? So T1 cannot. What was it? Sorry, I got confused. Yeah. So this integral means T1 direction cannot exceed T2 coordinate. So which means that so you have to integrate over this direction, this region, As you can easily see, the coordinate here. So T2 is bigger than T1, right? T2 coordinate is bigger than T1 coordinate, right? So T1 should be less than T2. Okay. So always this region T1 is less than T2. Okay? But however, this integral is the same as this integral. Okay. You just swap the coordinate T2 and T1. So you just T2 and T1 is a dummy variable. So you can just swap it. So therefore, this can be understood 1/2 of T0 T and T and T0 dt to dt1 and hi T2 hi T1. Okay. So here, as you can easily see, so T0 to T. T0 to T means you just integrate the whole square here and divide by 2. Is it okay? So please, there's a difference between the integral region. Okay? T0 to T2 in the left hand side, but only on the right hand side T0 to T. So therefore, right hand side you just integrate whole square and divide by 2 because the contribution between upper triangle and lower triangle is the same. Okay, and you can do the same game. If you look at the cubic term is essentially what we have is the really cube. That's why it's called cubic. And so the region we need to integrate over is, so this region is essentially integral over, depending on how you take the, but this triangle, the upper triangle. Okay. But the region is, but the way you, I mean, you can cut this triangle in 1/3 factorial way. So that you can just, if you combine this pyramid 3 factorial way, you can just exhaust all the cube. Okay? So therefore, what we have is this U operator, this solution. Maybe, yeah. U operator. Okay, maybe it's a bit. Is the 1 plus minus I T naught T and then dt. Half minus 1 I and then T naught T dt time order. Oh my goodness. Okay, I told you wrong. Sorry, I was not careful about it. So you have to be careful about the order, as I mentioned many times. Where's the erasing? So here you have to be careful. So as I mentioned, so this is time order. So usually, so as I mentioned, this H, the different time HI do not commute. HI's at the different time do not commute. And here, T2 is bigger than T1. So therefore, T2 is the, how to say, future from T1, which means, therefore, but here when you integrate here, so you have to swap the order. Okay, you have to swap the order. So that will be taking care of this time ordering. Okay? So you have to include T. Otherwise, you cannot. I mean, the order really is wrong order. So you have to be careful about that because of this non-commutativeness of interacting Hamiltonian. Sorry. So I didn't emphasize this part. And so on. Minus I to the 3 factorial, T naught T, dt1, dt2, dt3. So if you put that in time order, you don't need to worry about this, you don't need to worry about the dummy variable, order of dummy variable. And so on. So this can be understood is exponential of the integral of minus I T naught to T dt like this. So you can just repackage, and then you have to put time ordering. Okay. So here it's just so you know, right? Exponential ix is equal to 1 plus ix. I'm writing roughly, right? the factorial and so on. So, but you have to be careful about the time ordering. Time ordering. Sorry, this is square and sorry, I miss. This is square and this is cube. Sorry. Yeah. So using Taylor expansion of e to the x, or maybe I don't need x I here. By using Taylor expansion of e to the x, and you can repackage this infinite many term into the exponential. But since there is time ordering, you have to put time ordering here. Okay. Any question at this moment? So therefore, this very simple stuff. So this UT, the difference between Heisenberg operator and interacting picture operator are related by this U operator. And the U operator can be written very elegant form. Just e to the some integral of interacting Hamiltonian with time ordering. It's a very simple expression. So which is very good sign. Okay. Any question at this moment? So now, we want to understand the relationship between true vacuum in interacting theory and the vacuum of the free theory. So now, first let's see H is the full Hamiltonian. So N is the basis of it. Whatever. R span the basis. Span the basis of the eigenstate. Of full Hamiltonian. Hamiltonian H, which is H naught plus H int. So, and we write down that H of n is En. That's the basis of the full Hamiltonian. So now, then, of course, we will do the usual stuff. Which acts on 0. So this 0 is the vacuum of the free theory, and we can just write down this one is e to the minus h e. So n, so that span of n. So now this means that the identity operator can be written as the usual manner in quantum mechanics, like this way. So we insert identity operator into here and take inner product. And then we know that the ground state of this full Hamiltonian is omega. So that we just write down explicitly this e to the minus I e omega e omega and then omega and 0 and then plus So we just from here n runs all the states, but we just extract only the true vacuum of the interaction theory and the rest. Okay. And of course the En is the E omega. So therefore since this is ground state state energy. And the other is just excited states. These are excited states. And suppose, we want to get rid of the this contribution to see the relation between 0 and the omega. So to do that, we send, to drop this term, so we send capital T goes to infinity times 1 minus I epsilon. So to do that, if you do that, so you have a minus I times minus I is equal to minus sign, and then infinity times something infinity times the E omega and En. So there is a difference between En and E omega because En is the excited state. So therefore, the most of the states, all the excited states become exponential small. Contribution becomes exponential small when you send T goes to infinity minus I epsilon. Okay, do you understand what I mean? Since minus I times minus I is equal to minus sign. If you go to T is infinity, since En is bigger than E omega, so what's left is this contribution is dominant, becomes dominant. So therefore, relation between omega and 0 can be written as follows. Limit T goes to infinity 1 minus I epsilon e to the minus I e omega T omega 0. This is the inverse. So this part is just scalar quantity. It's just number. E to the minus I h t 0. So that's the relation between capital omega and then the vacuum free theory. And then we will do the small trick, which is called gamma law theorem. It's just a small trick, but anyway, this manipulation is given by gamma law. By the way, so this series is called Dyson series. So this series is called Dyson series. So as I mentioned, at the beginning of the lecture, so the Feynman, Schwing, and Tomonaga try to formulate the perturbation theory like this way, but perturbation theory and Dyson actually show that they are equivalent. Their formulation are all equivalent, and Dyson's formulation is this one. So that's why it's called Dyson series. So what we are going to do is just since T is very large, we can shift T a small amount. So therefore, we just shift the we can shift limit T goes to infinity 1 minus I epsilon. So we shift a little small amount of t naught. So it's okay, but because I mean t essentially goes to infinity. So therefore shift doesn't matter. And since we know the so this is a vacuum of the free theory, we can freely put the e to the IH in fact. So this can be written, so let me shift a little bit because the formula becomes a bit long. T goes to T infinity 1 minus I epsilon e to the minus I e omega. Okay. E to the minus I h t naught minus so here I put this operator, new operator. We already knew that the h naught acts on 0, you get 0 because it's free theory. Okay, so we already knew that so this guy is a free, the vacuum of free theory. H naught acts on 0 is just at 0. Okay, that's the definition. Therefore, even if you put the insert, this term is okay because it's just 1. H naught acts on 0 is just 1, right? And then we just manipulate. So we notice that this guy is indeed, the whole thing is indeed, the whole thing indeed U operator. So therefore, we write this one is limit t goes to infinity 1 minus I epsilon e to e minus I e omega t naught minus t omega. Oh, sorry, I need the inverse in up there. Sorry. So the reason why I just wrote down the minus t here is that this is the operation from, how to say, minus infinity to t naught. So this time evolution from minus infinity to t naught. That's what it means. That's why I just wrote the sign like this way, okay, to make it explicit. And this is this omega relation. So this means that so at the infinity many paths, it's a long time path. You can just have the free theory, free vacuum, and let the evolve by U operator. U is just this guy. U is just this guy. By time evolution dictated by this guy, and up to normalization, you get the true vacuum. That's what it means. Okay. So long time pass, you can have just free vacuum, okay, and let this free vacuum evolve by this U operator, and then you get the true vacuum of interaction theory. That's what it means. So this is called Gell-Mann law theory. Great particle physicist, Gell-Mann and Low. Okay. Any question at this moment? Okay, so now we are ready to. So that's the relation between capital true bucket and the free bucket. And then now we are ready to compute the 2-point function or multiple function. So we want to compute this. This 2-point function. Okay. So now we suppose x naught is y naught for simplicity. For time ordering, so here it's time ordering. So, but if this is satisfied, we don't need to worry about the order. Suppose then this guy is equal to, it's going to be a long formula, so I want to write down the bottom. And then, so of course, if you take the Hermitian conjugate, you just do the Hermitian conjugate, this operator. So then what we have is the 0 ut x naught and then phi of x, phi of y, u what I'm doing here? Sorry, I just got confused. Okay, so that's fine. U t naught minus t, and then 0, and some normalization. Normalization is super boring one. So normalization is essentially e to the minus I e omega t minus t naught 0 and omega inverse, and then e to the minus I e omega t naught minus t and the omega and 0 and inverse. Okay, so this is the case, and we just write down this one is the this one is equal to u to the x naught t naught interaction x, and then u x naught and t naught. Sorry, one of them should be dagger. And this one I can just write down the phi I. So that's a really relation between Heisenberg picture and induction picture. This one is equal to u y naught t naught and then u y naught t naught dagger. Okay. So that's the relation between induction picture. So recall that this part is this omega, left omega, and the right part is this one, this guy. By using this Gauss law theorem, so you just swap to get the yellow. And then we use this blue relation, and then let's use full color. Purple guy is this guy. Okay. Relation and repackage it. So note that the sign of T naught is different because minus times minus and plus, but here minus sign is so they cancel. And this is the Hermitian commute difference. So you just have square. So the overall factor is indeed limit of T goes to infinity 1 minus I epsilon 0 omega square e to the minus I e omega to t inverse. That's the overall factor. So it's just it's not important. So as we will see, and then we have you can combine. This time this will give you the operator which is t to t naught, and then phi I of x, and then u x naught and y naught. If you combine this time, this will give you x naught to y naught, and then we have a y operator interaction picture and a u, and then I'm very sorry. I think do I write the 0 here? So 0. P and not P. So this times this will combine into this guy. Okay? So it's a very nice form. So this means that so you start with 0 and let this state involved by this U operator, and you encounter interaction picture of the phi, and let this state evolve by U operator from Y naught to X naught as the time goes by, and then you hit this operator at the time X naught, and then so then here it's X naught. Sorry. And let this operator goes to X naught to T or time infinity, and it just you encounter the vacuum at the infinity future. So that's what it means. And we should normalize properly. And then we are going to normalize. So there's a normalization factor here, but I think if you use the following, so we can just normalize the true vacuum as omega like this way. That's actually kind of a bit strange. Maybe it's okay. Yeah, it's okay. So you normalize true vacuum like this way. Then true vacuum is just you just take the combination of this side and the Hermitian conjugate, which means the limit t goes to infinity 1 minus I epsilon 0. So you have the same factor. The same factor e to e minus I e omega to t minus 1, but the 0 u t and minus t and 0. So that's what we have for inner product of the omega. So note that here I use this one is equal to u t T naught, U T naught T. That's pretty neat. So therefore, so if you take a ratio between them, what we have is that the two-point function in interaction theory is indeed given by so 0 U T and T x0 and phi I of x U x0 y naught phi I of y U phi naught minus t and 0 in numerator, and denominator you have a simple factor. So if you take a ratio, so you can get rid of this slightly annoying factor, ugly factor. Okay. So this is a relation, and this can be written. So here we assume that the x naught is greater than y naught, and so on. But what if you swap the order? This can be easily done by the following trick. Just use time order. So therefore, time order two-point correlation function is indeed given by its super simple form at the end of the day of this manipulation. 0 time order phi I of x, phi I of y, okay. So here, so you have ut x naught, u x naught, y naught minus t, and then you just put the phi I at the appropriate position. And this one, this operation, this is really time ordered operator. But if you swap the order x naught, y naught, so you have to swap the x and y. But that can be everything is taken care of once you put t here, because everything, this operator should be arranged in such a way that everything is time ordered. So that's what it means, this t. Okay, so this is super simple form. And in particular, so we already knew that the U operator is exponential of the interacting Hamiltonian. So therefore, we can do the same thing for multi-point correlation function. T goes to infinity 1 minus I epsilon, and then 0 time order phi x1 phi xn e to e minus I minus t to t h I t t and 0 and 0 e to the minus I minus t to t h I, like this. And I think I should put t here, so sorry. Be careful, this t is not the time t, sorry, this is time order. So maybe I should use some fancy notation, some t, something like this way. I don't know. Maybe time ordering here is the fancy quality, maybe. So be careful. This is not time t. So not this t. So I think in lecture note it's the same font, and maybe I should change the time ordering notation a little bit, quality or something. Sorry. Okay. So now for correlation function of phi, this true Heisenberg operator phi and true vacuum in interaction theory can be written in terms of, sorry, there is an I here, interaction operator. So interaction picture operator phi I, and then interacting Hamiltonian hi. Okay? And then this zero is a vacuum of free theory. Okay? So therefore, this is the relation between correlation function interacting theory can be written in terms of interaction picture operator and the free vacuum. Any question at this moment? And we already know this guy is in fact is equal to 1 plus minus I t hi of t dt, and this hi has the lambda, right? So if it is the phi 4 theory, it has lambda for factorial phi to the fourth with appropriately normalized e to this I forgot e to the some Hamiltonian you have to use. Minus I h naught whatever 2t whatever, anyway t I h naught t or something. So this it contains lambda in first term, and second term we have minus I of minus t to t dt1 and dt2 and time order hi and t1 hi of t2 and so t2 this t, okay, time order, and here you have lambda coming from here and lambda coming from here, so therefore this is lambda order lambda squared, okay, and so on. So therefore if you expand this U operator, you have a perturbation theory 1 plus lambda squared plus lambda cube and so on, and that's will be encoded. That will encode information quantum correction. And then from now on, so we want to evaluate each quantum correction at each coupling constant order, lambda to some powers order. So that to evaluate that, you will use so-called Feynman diagram technique. I think it's a good place. Oh gosh, you kick the camera so that the recording is not.
Oh, sorry.
Okay, anyway, so let's take a break for 10 minutes. Some of the blackboard is not shown. So when you sit, you have to be in the front, you have to be careful. Okay. So please pick the homework. Otherwise, I have to bring it back at the office.
这个吧，如果你尽量都做这个只是把这个带进去，这个是啥？
Yeah. But it's supposed to be the same.
This also can be like but not like this time but time like
这个是长。
所以它其实是但你实际上算这个真实实际上算的是你只要算这个时候在里边是你要就是去在这个时间插入按照时间去插你要just interval
I will explain this part. I will explain this part later.
Right.
So you just need to wait. So it's not the relation between the prima path integral and this picture. It's not the relation. Your question is why the time integral is shifted by I. That's your question.
Yes. I don't know how to say it.
No. My question is that are you asking why do you introduce the prima path integral? It's about the path integral? Do you need to ask the question? So you want to ask how to take this epsilon basically? How to take care of epsilon?
No. I want to ask why, how can if we use the path integral to derive the two-part function, things that
But this part I will explain later. H naught is max on 0, it's just 0. H naught is the free Hamiltonian. This is free factor. So the alpha eigenvalue is zero. It's just one. Oh, okay. No. Here, lambda and gamma. So it's alpha, so it can be down. If you lower the indices, it becomes G. No, I mean, the lambda prime, it has proportional G and lambda prime. And we have lower the indices. Just multiply delta lambda. So if you write down this one as we so for instance, alpha gamma is this sum of gamma. Alpha gamma and lower gamma, then I have to use this lambda, I call it lambda, then zero. Then this should be equal to G lambda gamma alpha gamma and then something. And at the end of the day, if you act the G acts on this one, at the end of the day, what you get is this lambda. Alpha lambda. But here you also same. So alpha gamma delta lambda gamma is equal to alpha lambda. So if you take contraction gamma, you get the lambda lower. And the result is the same. And then I will take a picture of these two students. If you know this guy's please take. Okay.
I should have asked you earlier.
Hey, if it is homework, you can ask me at the end of the lecture.
Okay.
So now, so we're gonna okay, so we're going to learn Feynman diagram techniques from now on. So as I mentioned, so what we want to, if you want to evaluate the correlation function in interacting theory, what we need to do is just expand this U operator in terms of lambda coupling constant expansion, and then evaluate the in the numerator. So that what we want is essentially essentially we want to evaluate t and phi I of x1 phi I xn. So we want to evaluate this guy. So we want to evaluate this guy. And we know this interaction feature operator admits the free field expansion dqt 2 pi cube, and do I have a spell thing? Okay, maybe I wrote a long formula at the beginning. Unfortunately, it's recorded. Sorry, so 1 over square root 2e is, I think I didn't put the square root at the beginning of the lecture. I don't remember. Now you can check, but it's already recorded. Okay. And again, so this part, we call it, so the annihilation operator, we call it phi of x plus. And the creation operator, phi I of minus of x, we call it. And then we decompose this phi I in the creation and annihilation operator, annihilation and the creation operator, and we will see the consequence. And then we just want to reshuffle the order. So suppose x naught is greater than y naught, or greater than or equal. Then the phi x, phi y, this time ordering is just of phi x and phi y is equal to phi minus x. Okay, we decompose like this way. Sorry. Excuse me. From now on, we drop this I indices. It's, for the sake of brevity, we will drop this indices subscript. So there's an I here. Implicitly, there's an I here. So then, so we already knew that the normal ordering operator put annihilation operator on the right and the creation operator to the left. Okay? So that's normal order. So this is normal ordering. So normal ordering just puts the annihilation operator right and creation operator to the left. And so we know that the this term is problematic because I mean here creation operator is right and the annihilation operator is left. That these three are okay. So therefore, what we have is that the cost is of the normal ordering can be compensated by adding this combinator. Okay. Am I correct? Yes. Yes. Okay. So this term will contain the term something like a phi minus phi plus, because the annihilation operator normal order always put the plus sign to the right and the minus sign to the left. Oh, sorry, I think I told you wrong, right and left. Sorry, but anyway, so therefore here phi plus minus phi plus minus phi minus phi minus phi plus. Therefore, they cancel, and what's left is this thing. Okay? And the reason why we are going to do is that since we know that if you sandwich normal operator, this is always 0. Okay? This is always 0. Because I mean, annihilation operator is right and the creation operator is left. So so therefore, if you sandwich by the vacuum, so this term does not contribute; it's just 0. Okay? So therefore, what we have and then so if you drop this condition, what we have is that so here we assume this condition, but if you don't put this constraint, so what we have is T of phi x phi y is equal to the normal ordering like this. So therefore, but we know how to compute this guy. So we already knew how to evaluate this guy if you sandwich by vacuum. So if you 0 t phi x phi of y of 0 And this is, since this guy did not contribute to the correlation function, as I mentioned, if you sandwich by vacuum, sandwich by vacuum, and then so we have this this term we already evaluated in free theory, and we know this is given by one propagator f x minus y. Is it okay? Are you guys following? Any question at this moment? Is it okay? Okay. So we can do the same game. So we can do the same game that the so if you have the for instance the time ordering of phi 1, phi 2, phi 3, then what we have is the normal ordering of okay. Sorry, n is the n is the normal ordering, but anyway, so normal ordering of phi 1, phi 2, phi 3, and then plus let's see, this commutator phi 1 plus phi 2 and normal of phi 3 and minus, sorry. So here and sorry plus am I doing correct thing? Hopefully. Oh gosh, I think it's better to not to use this. This is a bit confusing. So because of this, I mean, it's a bit confusing, sorry. So let's consider 4-point function first. Plus and so on. So we just take the here we consider often write down like this way, weak contraction like this way. So this is a term for commutation and so on. So you just consider all possible contractions one has to take, and then at the end of the day we want to evaluate this guy. And so if you have normal ordering operator, this if you sandwich by vacuum, this normal ordering operator always annihilates the vacuum. So therefore, what we need to do is essentially if you have phi 1, phi 2, phi 3, phi 4, and you need to contract twice. So this will give you the term something like a phi 1 plus and a phi 2 minus, and then phi 3 plus and a phi 4 minus, and so on. And of course, we need to be careful about the time ordering. So you need to sometimes, depending on which one is the future or past, depending, you have to put the stator. But essentially, here, if you sandwich by the vacuum, essentially this will give you propagator. So this, once you contract and taking care of by time ordering, so this contraction will give one propagator. That we already knew from Q. So therefore, what we have is that the all possible contraction. So I'm going to schematic. Hopefully I can write that everything. And then what else? What else? Contraction, right? Oh, this is all. Sorry, this is all. Contraction you can take. Oops. Then let me write down the bottom. And this will give you the propagator. So from here. So this will give propagator df x1 minus x2. This contraction will give you x3 minus x4. Okay? That we already knew because of this commutator. So yeah, of course, everything. So you have to care about time ordering. And next term, it's super simple. You just swap the variable. So this is the result after weak contraction. And then Feynman introduced the notion how to pictorial way to describe this diagram, and Feynman just introduced the following notation. So we have x1, whatever. What was the notation? 1, 2, 3, 4. So this is essentially x1, x2, x3, x4. And the first term is the x1 and x2 are connected as a propagator. And 3, 4, and then next is 4, like this way. 1, 2, 3, 4, like this. So this is the simplest example of the Feynman diagram. It's super simple. And we're going to apply this one into the multiple in the perturbation theory. Let's do that. Any question at this moment? It's going to be a bit more interesting because here, if you understand the Feynman, how to draw the Feynman diagram, you become like a physicist, right? You feel like you become a physicist if you understand the Feynman diagram. Anyway, the Feynman diagram are drawn everywhere. Does our physics building have a Feynman diagram in the building? For instance, if you go to the US, of course, Caltech. When you go to Caltech physics building, fourth floor, everything Feynman diagram. And even Simon Center has the count. So if you understand how to draw the Feynman diagram, you feel like you become a physicist. Okay, so let's apply this Feynman diagram technique to potential theory for two-point function. So and so on. Okay. Here is just the first term of minus infinity to infinity, whatever. Anyway, here is just hi of t of dt minus I. So that's what we have. So this part is the first order, and of course the perturbation theory of lambda square. So we just ignore it first. And let's write down pictorially how to do the weak contraction for this term. So the first term too simple to do the weak contraction because there's only one way. So this will give you give rise to df x minus y. It's super simple. Okay, then let's do the next term. The first one is the same way. Same way means so first you contract this one, and then contract this one, and contract this one. Okay. Or so this term will give you this orange will give you the following diagram. So we just start from x to y. So then x to y. And there's a z here. And the z cross itself, which means the z cross itself. So one of the contraction will give you this loop, and the other contraction will give you another loop. Okay? Z to z. Okay? So this is a kind of boring contraction. The next one is a much more interesting one. Okay, so I will use blue. So contraction is x to z, and then y to z, and then you contract like this. So now what we have is that the x to z, y to z, and z to z. Okay? You understand? Do you understand how to contract? X to phi x to phi z, so that will give you this line. Phi y to phi z, that will give you this line. And the phi z to phi z, that will give you this loop. Okay? So this is the but you have to be a bit careful about the how to contract. There's a lots of ways to give you orange in the, and I'm going to erase this orange because it's confusing. Okay. So this orange term will give you the following factor: minus I lambda over 4 factorial df x minus y So, but however, you have to be careful. So here, there are lots of ways to contract the same term. You can do this kind of contraction. So this is another contraction that will give you the same term, same diagram. Another way is this to this, this to this. Okay? So therefore, there's 3 ways of doing contraction that will give you the same term. Do you understand? Okay. Next. Is it hard to see this blue? But I hope it's okay. It's bearable. Is it okay? No?
It's a bit hard to see.
It's hard to see. Okay, next time. Okay, this time please bear with me. I already used blue, so next time I will choose a different color. So this term will give you this kind of term. But now we need to be careful about how many ways of which contraction will give you the same term. So phi x contract with this guy first, but no one prohibits you to contract with this phi x to this phi z. Second one. There's the 4 choices. Okay. Next one is phi 1 can be contracted the other 3, right? So for the other 3. Once you pick one x, pick one of them.
Oh no! Oh my god. Sorry. Should not sitting from here.
Okay, hopefully it's okay. So therefore, there's a phi x has a 4 partner. There's a choice of partner 4 way. Once you pick one, x pick one of them, y has a 3 partner. So therefore, 3 choices of partners. So therefore 4 times 3 will be here and plus. So this is these are cosymmetry factor. Okay. And these are called symmetry factor. These are called symmetry factor. These are called symmetry factor. Now, so to study symmetry factor, we go to higher order. So to understand the symmetry factor, we go to higher order. So for instance, we get the following. And we will see the following contraction. Oops, sorry. Okay, so this contraction will give rise to the following. So x to the z, and then z goes to z. There's a one loop here, and z goes to. Oh, sorry. This should be w, and this should be what? U. So z goes to z, that will give you a loop. Z goes to w, z goes to w. And y indeed goes to w. So now for external h. And then y goes to, sorry, what I'm doing here? W goes to u. W goes to u. Another w goes to u, so which means another path. And then u goes to u, which give you a loop. Okay. And the question is how many terms, how many way of this contraction will give you this diagram. So note that if you have a insertion of the phi x 2-point correlation function, x and y will always appear as the endpoints of this diagram. Okay, so the external insertion will give you endpoints. Okay. So first of all, to the 3 factorial way to interchange, 3 factorial way interchange z, w, u. So z, w, u are the dummy variable. Okay. So therefore, you can exchange variable z, w, u so freely. So I mean, you can call z as a u, and then u as a z. So then you can do the different way of contraction. So that will give you the 3 factorial, and then so x can contract. So when x contracts z variable, there is a choice of 4 partner. So 4 partner, and then so another one out of 3 can how to say find a part of w. Okay. Then after all, you get this root. So therefore 4 times 3. Okay. So x can find a choice of 4 partner, and the other 3, 1 out of 3 can have a partner of w. So that will give you 3. And then so when this z try to find a partner, so you have 4 choices in w. So you have 4. Once z find a partner, so y have 3 choices. 3 choices. Okay. So therefore you have to multiply 3, and then again. So what's left is 2. Okay. And then let's see. So 2 out of 1 has 4 choices. 4 choices of choosing u. So therefore you have to multiply by 2. And then the same thing. So once this guy tried to find a partner, there's 4 choices, and the other one have 3 choices, and then the rest will be closed. Okay. Okay, so that's the case. Oh, I see. Okay, so then, so there's a W and the U contraction. So there's a two-way to do that, but we overcounted. I mean, this guy and this contraction and this contraction, and is the same as this contraction and this contraction. That will give you the same diagram. So therefore you have to divide by 2. Okay, so that's the symmetry factor, and then you have 4 factorial to the cube. So you have to have a 4 factorial to the cube. That's a symmetry factor. Sorry, and also 1 over 3 factorial here. 3 factorial, and that will give you 8. That will give you 8. Is it okay? Are you following? Do you have any question? Is it okay?
1 over 8.
1 over 8. Thank you very much. That's true. 3 factorial cancel, and from here 2, from here just 1 and 2 and 1 over 8. Thank you very much. Okay, so this is the symmetry factor of this diagram, and we would like to understand this symmetry factor. So first of all, this can be understood 1 over 2.2.2. And first 2 really coming from 4 times 3 divided by 4 factorial. Okay, so that is really coming from this factor. And this factor can be understood as the and also so this factor can be understood some symmetry that so this can be swapped. So this root can be swapped like this way. It will give you same diagram. So therefore, these first two coming from some symmetry of this diagram that swap this root. And the second one is also same. So this 4 times 3 is coming from this u integration. So 4 times 3 divided by 4 factorial will give you this choice of u. So the u from u, so you have even if you swap this ribbon, you will get the same diagram. So therefore, this 2 factor really come from the symmetry of this diagram. So that if you swap this one. And now the other factor 2 coming from connecting this 1 over 2. Okay, this 1 over 2 is really the way how you contract with w and u. So w and u. There's even if you do the same how to say the other contraction, that will give you the same factor. So which means that even if you so there's a line from W to U and W to U, 2 lines, but even if you swap them, the diagram doesn't change. So therefore, the other 2 really coming from the swapping the 2 card from W to U in the exchange of the W and U. So that's the symmetry factor, can be understood. Even though it's super complicated. But so this symmetry factor can be understood as some symmetry of diagram. And then in lecture note, I just give you the some example of the symmetry factor. For instance, did I already erase it? Oh, good. For instance, this will give you symmetry factor 1 over 2, right? But this 1 over 2 really comes from even if you rotate 180 degrees in the the vertical direction to the black pole, it's okay. So if you swap it, so that factor will give you 1 over 2. Here you have a 4 times 2. So 4 times 2. It can be understood 2 times 2 times 2. So one is you just swap these two, this ribbon, and the other is the other factor 2 comes from the bottom ribbon. You just swap, you get the 2, and the other factor 2 you just swap upper ribbon and the lower ribbon like this way. That will give you symmetry factor. Do you understand? But if you don't, if you get confused, you always just count how many ways of do the weak contraction. You just count, then you get the symmetry factor. Anyway, so that's how you get the symmetry factor. Do you have any question about symmetry factor? If not, I will move on. Where should I erase? Maybe I should erase it. Any question at this moment? Is it okay? Okay, let me move on. So far we talk about the numerator. So as you recall, so this is the correlation function in interaction theory, omega. We now we are looking at some example of the evaluating the numerator, and now we are looking at the denominator. We are going to look at the denominator. So the denominator is equal to 1 plus and so on. Okay. So then, again, so we can just contract like this way, and that will give you this kind of diagram. So this is Z, and this contraction will give you loop, and this contraction will give you loop. And we know the symmetry factor here is just same as over there, 1/4 times 2 or whatever, 1/8. We can do the same thing here. Many ways. I mean, and the simplest way is this one, right? Okay, so we can do this kind of stuff, and that will give you Z and W, and like this way. That will give you 4 lines be from Z to W. Okay? Is it okay? And then I cannot somehow use the orange. Let's use yellow. The next thing we can do is that, for instance, so this kind of diagram would be you start with Z, and this will give a loop, and this will give a line from curve from Z to W, and another Z to W, and this will give a loop of that W like this way. Okay. And then boring one. Unfortunately, I have to use purple. Let's use purple. The boring one is this one. Well, this will give you two of this guy. Okay, and then you just need to count the symmetry factor. Okay, so therefore, denominator is always give you this kind of like a there's no extra endpoints. There's no like endpoint like this way, external points like this way. Always the diagram is closed itself. Okay. The diagram should be closed itself. Okay. And let's first look at the symmetry factor of this 8. So this is the 8 diagram. Okay. So we know that this way we start with the 1 plus symmetry factor, this guy. But here we can swap the role of Z and W, right? Z and W. So that will give you. So this means this way means this will give you the factor. Sorry, the factor. Or the minus I to the lambda, we know 8. 8 is symmetry factor. 1 over 8 is symmetry factor, the same as over there. And then dz and df, 0 and 0. 0 means z minus z. Okay. So this is the factor. And this purple one will give you the same factor, and this another purple one will give the same factor. But now we can swap the role of Z and W. Okay. So that will give you 1 over 2 of 8 and 8. So in other words, you can swap the role of Z and W like this way. And the same thing will happen. So this will give you 3 factorial and 8, 8, 8 in lambda to the cube and so on. So therefore this is essentially equal to exponential of this 8. Exponential of 8. 8 diagonals. Okay, so that's vacuum diagram. So the same thing happened for the other diagram. The same thing happened in the other diagram. So therefore, sorry. So this is not the equality. So this contain. So denominator. What is it? Contain. Yeah, contain. So denominator contain of this factor. the same thing happened for the other diagram. So at the end of the day, what we have is that this is equal to exponential of all possible whatever diagram, whatever cross diagram, and so on. So that's the denominator contribution in fact. And now, so here to compute to put two-point correlation function interaction theory, so we have to divide numerator by denominator. And here we already knew that numerator can have the external line, the diagram which has the endpoint times without endpoint. Okay? So essentially, as you can easily imagine, this term will cancel with this diagram. As you can easily imagine. So if you go to higher one, in addition to this loop, this kind of loop will show up. And also, if you go to this times this, and also if you go to higher one, so this times whatever, this will show up. And this times this one also show up. If you go to higher order, and this times this one show up. Do you understand what I mean? That will cancel with these three. That will cancel these three. So therefore, what we have is the following. Let me get some water. So numerator is equal to sum of connected diagram with two endpoints, x and y, times denominator. So this is essentially equal to 0 t e to the minus I h I dt 0. Okay. So therefore, so this is equal to sum of connected diagram with two endpoints, x and y. And you can play the same thing happen for multi-point function. So omega t phi 1 dot phi n omega is equal to the sum of connected. Oh my goodness. Okay, let's with n endpoints. x1 dot xn. That's so that's the conclusion. Any question? Okay. Okay, it's a good pace. Is it too fast? Or it's okay? So now, so given a diagram, so let's see how to read off the corresponding term. So we already knew that the this diagram will give you this kind of integral, right? Likewise, so this term will give you this one. But essentially, what we are interested in is only the one which is the connected with endpoint. Okay. So, and we ignore these vacuum bubbles. So this closed diagram is called vacuum bubbles. Sorry, I didn't mention it. So we're not interested in these vacuum bubbles because they counter each other in numerator and denominator. Okay. Okay, so let's give you final rule. Final rule means that given the diagram, how to write down the corresponding term. That's final rule. So be careful. So be careful. So this is only for FIFO theory. So the other theory, the rule will become different. Final rule will be different. So this is specific for FIFO theory. So here, when you consider correlation function, something like a phi xi1 equal to phi xn e to the minus I hi dt 0. So each insertion of phi, so you have an external point xi, that's we already see, and then here some internal internal points Ci for interaction. So as we saw, or unfortunately I already erased, so these Z or W are all coming from interaction term. Okay, all come from interaction term. And then here we assign the term minus I to the lambda. Minus I to the lambda. So for instance, we have a diagram like this way. X, Y, X and X1, X2 are the external point, and Z1 is the internal point. And if you have an internal point, it always proportional to I lambda. That's what it means. And if you have the other internal point Z2, you have a square. Okay? Square. And then so just draw a line. Between points until and every so every external line has only connected one line, but internal line, internal point should be connected four line. So in this case, 1, 2, 3, 4. Okay, this internal line is 1, 2, 3, 4 because we have 5 to the 4th interaction in the for. So always okay. 4 factor is okay. So for internal points, so we all assign this one. So therefore, this 5, 4 should create 4 lines at the internal points. Okay. And then let me continue here. Then for line, x to y from assign corresponds to assign df x minus y, which is this one, the one we derived. And then at the end of the day, so you have to divide it by symmetry factor of the diagonal. That's it. That's final diagram for position space. I think I should call it in position space. So that's a row. Okay. So now, okay, let's see. And since if you have this kind of factor loop, so this kind of df z1 minus z2 minus z2 will show up, which is equal to df of 0. This kind of stuff will show up. Okay. But so this one is kind of problematic, which is diverging, but this will be treated as a renormalization later. So this is the subject renormalization treated by renormalization. So this is a future subject. As we study quantum field theory in this course, we would learn how to treat this df0, df of 0, which is created by loop diagram. So this is really treated by loop diagram, created by loop diagram, and also. Do I miss something? I think it's okay. So I think, yeah, we can just, to simplify the expression of this after Feynman rule, we can perform the position integral. So this is the perform position integral. D I for every internal point. That's also one can add. If you add this one, so internal point, you always have so this kind of diagram, the internal line. And then we have whatever P1, P2, P3, P4. So be careful about the orientation of the arrow. So this is P1 is incoming, and then P3 and P4 are outgoing from the internal point, and that will give you P4Z E3I P1Z plus I to the P2Z minus I to the P3Z minus I to the P4Z. So that's P3 and P4 are minus sign because it's outgoing, and the P1 and P2 are incoming. So therefore the sign will be determined like this way, and then that will give you the conservation of angular momentum at each vertex. Okay. Okay. And in fact, this is positional space, but if you go to momentum space, so let's consider the whatever. So this quantity, so do I erase it or do I still keep it? Oh yeah, this one. Let's call this quantity is g x1. It's a function of the external points. And we can perform the Fourier integral of this guy. So if you do the Fourier integral, the rule become much simpler. So here, so what we are doing is that there is something, some diagrams here, something going on, and then x1, x whatever k, xk, xn, and you have a p1, p, k. Like this. And then the final rule for position space. Position space as follows. So Feynman rule for position space is as follows. So you can just write down so given each line with directed you assign the following. You assign the following factor. Okay. And each vertex and at each internal vertex we assign 2 pi to the fourth minus I lambda the alpha function of 4 sum of incoming of pi and then outgoing of pi because of upper rule. Because of upper rule, and then what we have is for external vertex, each external vertex then you assign the following multiply e to the minus ipx for out. I think it's outgoing, and e to the ipx in incoming. Okay, and then perform integral for internal line, and divided by symmetry factor. So that's the rule for momentum space Feynman rule. Okay. And so side remark. So if you have a vacuum bubble, if you apply this one, we have to divide it by the for each vacuum bubble, we have the factor. We have the factor of the volume of spacetime. Volume Bt of spacetime. So this coming from, for instance, if you apply, so we already knew that so here, so for instance, if you look at this diagram, so if you apply this rule, so this has this factor dz to the force z delta to the force 0, right? So here, what we sorry, what I'm doing here? Oh no, sorry. What I'm doing, sorry. If you apply the above rule here, so here all the momentum here is the P1, and coming back P1, and go outgoing P2 and P2. This is outgoing, incoming P1 and P minus P1 cancel, right? And the P outgoing minus P2 and P2 will cancel. So therefore, the integral is just 1. E to the this momentum is just 1. So therefore, you have just the integral of the space-time volume. And this is, in fact, this is give you 2 pi to the force delta force 0, and this is equal to essentially this will give you infinity, of course. This will give you infinity, but however, this can be understood as the volume times time of the space-time. So as we saw in the Hamiltonian of the, so maybe recall that the Hamiltonian free scalar, you have something like a Hamilton density, I would say. Hamiltonian density, okay, Hamiltonian is okay. Hamiltonian, so the QP 2 pi of Q e to the P, sum of E, is it okay? No need minus, I think as far as delta Q 0, possibly some number 2 pi or something afterwards. And also this is plus sign for Hamiltonian free scalar theory. and we treat this delta function as a volume of the space, right? And we ignore, and then you just put the normal ordering and just get rid of it. So that's what we did. So this delta function is the same kind of this guy. So we just, if you do that, if you apply Feynman rule to this vacuum diagram, you always encounter this space integral without any without any this regulation. How to say? E to the some power. So therefore, that will give you that delta function always. Any question at this moment? I don't think. And then I don't think I have a time. Okay. Anyway. So, yeah, I think I should stop here. So there are two issues about this Feynman rule. So one is since we use so one issue is this delta function. So delta function. The other issue is we use the following. In fact, strictly speaking, we just t goes to infinity 1 minus I epsilon, and then minus t dz0, and space integral dqz, and e to the I minus I p1 p2 minus p3 p4 minus p4 of z. In fact, that integral I just wrote down d4 to the z, but in fact what we need to do is minus t to the t, which is the taking as an infinity times 1 minus epsilon, I epsilon. But if you strictly speaking, if you take the minus I epsilon times infinity, that will give you some problem in here. Because I mean, minus I times minus I will give you minus sign. And then t goes to infinity times epsilon, which means that either you go to t goes to infinity or minus infinity, this factor really becomes divergent. So this is the second issue. But unfortunately, time is up. So this delta function and then this issue will be treated at the beginning of next lecture. Okay, let's stop here. And then if you have questions, just tell me.